In this video, we're going to cover the first part of section 14.1, functions of several variables. Before we get into functions of several variables, I'll just remind you, consider a function of a single variable f of x. What does that mean? That means we plug in the independent variable x, or values in for that independent variable x, and we get out some output value y. Well, we have a similar thing happening for a function f of two variables. So here, though, we define it or denote it f of x comma y, where now we have two independent variables, x and y, and our output will usually be a third variable, z. So what do we say here? Well, the set D is the domain of f, where D is just each ordered pair x and y. The graph of the function f with domain D is just the set of all points x, y, and z in R3, where z is f of x, y. And of course, x comma y was in your domain. So let's try to determine what the domain is of a function of two variables and sketch that graph. Okay, so let's consider the function f of xy is equal to the square root of 9 minus x squared minus y squared. First thing we want to do is find the domain of the function and sketch that domain. So, if we're looking for the domain of this function, what do we need? Well, we know that the inside of a square root has to be equal or greater than 0, right? We can't have any negatives. So the domain is all values such that 9 minus x squared minus y squared is equal or greater than 0. Or, if we move the x squared and the y squared over, this is 9 is equal or greater than x squared plus y squared. We should recognize this as the equation for a circle with radius 3, but really we want all of the circles inside of that and equal to that. So if we want to sketch the domain here, we just draw a circle of radius 3, and our domain is everything inside of that. And so we've sketched our domain. Usually in a function of one variable, or not just usually, but in a function of one variable, our domain is some subset of the real line. Here, the domain is going to be some subset of the real plane, so a two-dimensional subset. All right, now let's try to sketch the graph of the function. Well, the function is really, we can think of this as z is equal to the square root of 9 minus x squared minus y squared, where our domain is everything inside that circle of radius 3. So let's draw a picture here. One, two, three, 2, 3, 1, 2, 3. And of course we also go up along the z-axis, 3. So let's draw a sphere of radius 3, except we're only going to draw the top half of the sphere. And it's everything on this top half of the sphere here. Why is it the top half? Well, this tells us that z is equal to the square root of 9 minus x squared minus y squared, and we don't have plus or minus here, so it's just the positive side. Right? We could also square both sides and get that z squared is equal to 9 minus x squared minus y squared, and recognize that this is the equation x squared plus y squared plus z squared is equal to 9, which is the sphere of radius 3, but again, just the top half of that sphere. All right, and so we drew that here. With, again, this is the back side. There. All right. Let's do one more example here. So we want to find and sketch the domain of the following functions. Well, let's look at this first one over here. We need the square root of y minus x squared in the numerator up here. So y minus x squared needs to be equal or greater than 0, or y is equal or greater than x squared. 1 minus x squared, So for the second part, 1 minus x squared, what can that not be? Well, that can't be 0. So in other words, 1 cannot equal x squared, or x cannot equal plus or minus 1. Okay? And once we're done with that, we were asked to sketch the domain. So let's go ahead and sketch that. So first we can sketch the y is equal or greater than x squared, or at least y is equal to x squared graph, except we're given that x can't be positive or negative 1. So let's sketch the graph of y equals x squared, except skip over when x is plus or minus 1. So that's why I drew the open circles at that point. We're not allowed to have x is equal to negative 1. We're not allowed to have x is equal to positive 1. But what is the region that fits this domain? Well, everything is allowed except y being less than x squared. So what is allowed is everything bigger than y is equal to x squared. Except, of course, again, along these dotted lines where x is plus or minus 1. And so we've sketched the domain of our function, of our two-variable function. Okay, let's try f of xy is equal to 1 over the natural log of 9 minus x squared minus 9y squared. Well, we cannot have anything that is negative or 0 inside a natural log. So we need 9 minus x squared minus 9y squared to be greater than 0. Or in other words, 9 is greater than x squared plus 9y squared. Okay. Let's go ahead and start drawing that here. This is an ellipse with specifically, if x is equal to 0, then y must be plus or minus 1, right? Let's consider 9 is equal to x squared plus 9y squared for just a moment to get the graph. So if x is 0, then y must be plus or minus 1. If y is 0, then this whole term goes to 0, and x is plus or minus 3. I'm going to draw a dotted ellipse here because we're not including these points because we don't have equality here. And then really this tells us that we can have everything inside of that because x squared plus 9y squared must be less than 9. So everything inside there, except we have one other issue, and that is that the denominator cannot be 0. So the natural log of 9 minus x squared minus 9y squared cannot be 0, But if this is 0 when the inside here is 1, so we cannot have this, which implies that we cannot have 8 is equal to x squared plus 9y squared. Well, what is that? Well, that is an ellipse that's just a little bit smaller than what we had. So this dotted ellipse cannot be in the domain either, but everything else inside the larger one, except for this dotted line, is allowed. So that is our domain, again, except leaving out that singular ellipse where 8 is equal to x squared plus 9y squared. And that'll end this first video.